Welcome to STEPCon20! We are here in beautiful sunny San Diego, home to surf, sand, beautiful beaches, and the world's most advanced technological donut? Really? A donut?
We'll get into this later. That's good.
On our way to General Atomics. I can't wait to see the show. Can you? Oh, come on, faster. The B3D National Fusion Facility. We are inside General Atomics. Come on, let's go. Come on. STEPCon20, the science show. And now to get these going, here is Professor Matters and Dr. Boom.
Good morning, and welcome to STEPCon20. I'm Professor Matters.
And I'm Dr. Boom. And we're here at the D3D Magnetic Fusion Facility.
We're here at the National Fusion Facility, and what we're going to show you is many of the science concepts that we use every day in our nuclear fusion research.
These concepts are basically we use them on a fusion reactor. So we're trying to create fusion to produce electricity with a limitless resource from our oceans. And so in order to do this, we have to heat a plasma up to about 150 to 200 million degrees centigrade.
150 million degrees? How do we hold on to that?
Well, you can't hold on to it with anything physical because it would melt and we wouldn't be able to get it so hot. So we use a magnetic field. We can find this plasma with a magnetic field, and that's how we keep it away from the vacuum vessel walls. Otherwise, it would cool off.
Vacuum vessel, gases, plasma. We're going to talk about states of matter today. We're going to talk about magnetism today. We're going to have a fun time. We're going to learn about how we can use some of these topics at our work, and hopefully you can use them in school. So welcome to STEPCon20, and we'll be back in a few minutes. Check this out. I have a little bit of something here. Watch this.
Whoa, look at that. Looks like Halloween.
Isn't that cool?
It's cool.
All right.
Welcome to the D3D pit. This is where the tokamak, heating systems, diagnostics, and all the other cool tools we use live. So behind me is a giant pumpkin. That is the tokamak. Inside the tokamak is where the plasma exists, and it gets super hot in there. On the outside of the pumpkin, you can see these big tan bands, and those are the magnetic field coils. Those create a kind of cage to keep the plasma confined, because if it wasn't confined, the plasma would get super hot, expand, and burn everything inside, which is bad. Here, we accelerate particles super fast and shoot them into the plasma. Overall, if we add enough of these particles, the overall temperature of the plasma increases, and hopefully we get fusion of the particles inside. As you can see, this is a huge room with a ton of different systems that are all super cool in their own way. Meantime, science is cool. Keep up with it.
Dr. Boom, this is the Magnet Lab.
Oh, Professor, indeed, I have all kinds of magnets. I have permanent magnets, I have electromagnets, and I have something else that'll be a surprise at the end.
Awesome. I'm going to step over here a little bit and let you tell us all about your magnets.
Okay, thank you very much. Now, I'll start out with, this is a permanent magnet. It's alnico magnet. It has aluminum, nickel, and cobalt. Now, most permanent magnets are made of some alloy. Okay, you can also make magnets out of iron, but I won't talk about that. And so this is a permanent magnet, and magnets have magnetic fields, and so we can't see them, but we can put iron filings around them so that it makes it so we can see what they look like. Okay, so I'm going to put this under this camera here, and I'm going to bring this magnet and put it underneath, and we're going to see what happens here as I bring it up close. Now, magnets have a north pole and a south pole, and that's because they always come in pairs. And the north pole is on one side and the south pole is on the other side. And you can see the iron filings are following the field lines. This is similar to how a plasma will follow the field lines. I'll move it around here and you can see how it goes here.
Oh, that's pretty cool.
You like that?
Yeah.
Okay, so permanent magnets are around us all over the place. We also have electromagnets. Now, we obviously can't change a permanent magnet's field force very easily, but we have electromagnets. And so I have an example here on the table. We have a bunch of compasses here. You can see they're all pointing towards the north.
What's actually pointing in that compass?
That compass is basically made up of a magnet itself, and it aligns itself with the magnetic field of the Earth, which is very low.
You mean that little needle in there is actually a magnet?
That little needle is a magnet, and it has a pole, north pole and south pole. North pole's on the red side, and the white south pole's on the white side. Now, when I turn on this electromagnetic coil, let's see what happens to the compasses. And so you can see that they align to the field lines. Now the field lines are represented by these blue lines here, and then the compasses are all aligned to those field lines. You see that? And so this is how a electromagnet will work, and this is what it results in. Now, what is an electromagnetic magnet made of? Well, it's turns of wire, and this is some wire that is just in a coil. And then we also have another coil here which has many more turns. So the more turns there are, the higher the field is, and the higher the current going through the turns, the higher the field is, the magnetic field is. And so
Dr. Boom, where is the magnetic field in that coil? Is it in the wire? Is it outside the wire?
No, the field is not in the wire. The field is outside the wire, and the field is just as you see it on this table. We have the field lines that go through the middle, and the strongest field is not in the middle, but it's out near the edges of the coil. And so
the main magnetic field, though, that we're concerned with actually goes through the center of that circle.
That's right. In fact, it looks like this.
Put that underneath.
Well, I can put it down here. Except it's not aligned with the field lines are here, and the coil is in the middle.
Okay, now I got it.
Okay, so now let me talk a little bit about permanent magnets. Okay, I have a little demo here. Let me bring it up. The way they create these permanent magnets is they take the material, like the Alnico magnets here, and they heat it up to very high temperatures, not so it's melted, but just so it's high temperatures, like 1,000 degrees C. And all the little poles in there, all the little atoms in there are randomly associated with direction, okay? So this is like a magnetic pole in there, and so is the south pole, north pole. And so what happens is they put a magnetic coil, electromagnetic coil above and below it, and they run a field through it. They turn on the coils and while it's hot, and then all the atoms align, and so that's how it becomes a permanent magnet. Then they cool the magnet material down, and all these atoms stay in the same direction. So that's how magnets form. So different materials have different strengths, and so the more poles they have, the stronger they are. And so we're going to show you more about electromagnets in the next couple of minutes, but until then.
Yeah, that's very cool. Those are permanent magnets. Right on.
Yeah, permanent magnets, and we have electromagnets as well. But we're going to show more about electromagnets after a break.
Okay.
Okay, everyone, let's check to see if lab and see what else is in store for us. Let's go back.
So, Dr. Boom, we were just talking a little bit about permanent magnets and electromagnets and the like. Do you have something here? I know that when I tried playing marbles with my brother, we were on some kind of metallic surface and my marble just wouldn't roll. Can you explain that maybe?
Well, if it was a glass marble, no. But if it's a magnet marble, I can tell you.
It was a magnet.
Oh, okay. So what we're going to talk about here is eddy currents. Now, eddy currents, you have to look up the definition, but eddy currents is what's called when a magnet induces a current in another material. And so basically what we're going to do here is we're going to show you what happens just straight away. I have a cue ball here. It's not a magnet. I'm going to roll it down this angle, and it has a slight angle here. I'm going to roll it down this aluminum angle, and we're going to see what happens. You can see it goes relatively fast, okay? So now I have a strong permanent magnet behind me here. I'm going to raise this up so it goes a little faster, and you can see here, oh, look at that. And all these compasses are reacting to the field going by. Okay, so what this does is as it moves, it has to be moving, it induces a current in the aluminum that produces a field that resists the movement of the field through it. And so this is basically how electricity is generated with a coil. You move a magnetic field through a coil, and a voltage is produced on the ends of the coil. And so you can see there, as the magnetic field moves through the aluminum, it slows it down. So it's like kind of your hand in the water, basically. But it's the field that's going through it, okay? So now I have another little demo here. We can do the same thing with this pipe here. I have a magnet in here in my hand. If I just drop it, you see it goes down and hits the aluminum really fast, okay? But if I drop it through the coil of the pipe here, let's see what happens. Ready? 3, 2, 1. Wow, it took a long time. So it's inducing a current in the magnet in the copper pipe, and that produces a magnetic field that resists the movement of the magnet through it. Let's do it again. 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. So about 5 seconds or so, and that's how long it would take. And so if I had a stronger magnetic field, it would take even longer. If I had a weaker magnetic field, it would take even shorter. And so if I dropped the metal ball through it, just as fast as if this was not there. Okay, so what else can we do with these things? Well, it turns out we have a coil here, 200 turns, just like the big one on the side, and it's small wire, so it's much lighter. So what we're going to do here is when I turn this on, the same field will be produced as you've seen here, and the field changes 60 times a second. So it starts on North Pole, South Pole, and then it changes back and forth. North Pole, South Pole, back and forth, really fast, okay? And so I'm going to turn it on, and we're going to see what happens on top of the aluminum. Ready? 3, 2, 1. Look at that. So now what's happening here is the field is changing 60 times a second. It's going through the aluminum, which is causing a current in the aluminum to produce a field that's changing 60 times a second. And guess what kind of fields repel each other? Like poles repel. So North Pole repels. South Pole repels.
So Dr. Boom, are you saying that when you switch on that coil, it's making a changing magnetic field, and that changing magnetic field effectively turns that aluminum plate into a magnet?
Exactly.
For the brief time that this magnet is on. That's pretty awesome.
And as you know, a non-moving field, like on this aluminum, there's nothing going on here.
Wow.
It doesn't stick. But if I had this stuck to a piece of iron.
Now, how far away can that magnetic field actually interact with other things?
Well, let's see. I have the magnet.
You're about
here.
a half a meter away.
About a half a meter, yeah, with this one. Sometimes a little closer. Okay, so I was in a lab about a year ago, and I was trying to figure out something else to do with these coils, and I put one of my spheres inside of an acrylic sphere, and then I turned on the magnet, okay? And so let's see what happens here. Now remember, this field is changing 60 times a second, the electromagnet, and the ball has a magnetic field, and look what happened.
That's awesome. That's an annoying sound.
So I thought, what could I do with this? It seems kind of useless, but it's pretty cool. So I thought I could turn it into a cat toy.
Oh, a cat would love to chase that.
A cat would be sitting here for days, just figure out what's going on.
All right,
There you
Dr.
have it.
Boom. Well, that's very cool. From the Magnet Lab, we talked about compasses and electromagnets. We talked about permanent magnets and how they're made. We talked about how far away you can be and still have a magnetic influence on things. Very awesome. Thank you, Dr. Boom.
Well, you're welcome there, Professor.
All right. I think that's it from the Magnet Lab today.
Okay. Hope you enjoyed our Magnet Lab.
Thank you.
This is a 1-to-1 scale model cross-section of the D3D tokamak. Tokamak is a Russian word since the Russians invented this device, which loosely translates to toroidal chamber with magnetic coils. Since this is a cross-section, take everything you see in this here and rotate it about a central axis, 360 degrees, and you will get the machine. Inside the perimeter, magnetic field lines form closed loops, because that's what we know about magnetic fields, is they form loops. And outside of the white line, the magnetic fields, the loops go through the wall. So particles that are inside travel along the field lines. The stronger the field, the tighter their circular motion about them, and they stay confined inside. But particles outside will leak out and impinge upon the wall. The biggest challenges for fusion energy now are keeping this reaction stable for long pulses and getting more energy out than we put in.
Professor, I was down at the beach just now, and I found this beach ball just blowing around the sand, and a thought came to me. This beach ball has atoms of air in it. I'm pretty sure that's air. It's not helium. It's not floating. And those atoms are all pushing against the sides at some speed.
Yes.
And so there's actually stuff going on inside this balloon that you can't see, you can't hear, you can't touch.
Yes, Dr. Boom, and I appreciate you coming to the States of Matter Lab. We're going to talk just about that today, about the energy that's inside moving particles, moving air molecules, just like that beach ball there. That's very cool. That's a great observation. Science is about observation, thinking about it, and then doing something, doing a demonstration, doing something to measure something. So what I have here, we're going to talk about what Dr. Boom has over there. He had gaseous form of the air. You know what I have, Dr. Boom? The air is made of nitrogen, oxygen, a little bit of something called argon, and a whole bunch of little, a small amount of other things.
Oh.
But mostly nitrogen.
Nitrogen.
We breathe it in and we breathe it out, and we don't use it, but it's there.
Okay.
Okay.
So what can we do with this nitrogen?
Now check this out. I actually have some liquefied nitrogen here. You know, if you get something really cold, gas is really cold, oftentimes they turn into a liquid.
Wow.
And we have some gaseous nitrogen that we've turned into a liquid. You know what temperature it is? Do you know what temperature this is?
I bet you it's really cold.
It's really cold at minus 196 degrees C.
Wow, that's really like below freezing.
It's very, very cold. Much colder than your freezer, much colder than the snow or the ice, much colder than the mountaintop. It's very cold. So I'm going to
Minus
pour.
196 degrees. Wow, what's it look like? Let's see.
Well, yeah, let's take it. Let's see what it looks like. Hold it here. There we go. So, don't get too close.
Wow. If you
So
got some
let's
on
see
you,
what it looks
happen?
like here. I'm going to pour some. Oh, look at that.
Wow, look at it. It's going all over. All that water vapor, you can see it condensing in the air. Wow.
That's a good observation, Dr. Boom. That is water vapor. That's not the nitrogen.
Oh.
What you see there is not the nitrogen.
It
That's
looks like it's
water
boiling.
vapor.
It's so cold. How could it be boiling?
It is boiling because at the temperature that this is, at minus 196 degrees C, the room here is very, very warm.
Oh.
Very, very warm. And in fact, let's take a look at what we can, if we take another look at this, we can pour this in a little baggie, and take a look at what this looks like. Again, it's very similar to what it looked like before. It's clear. It's colorless.
Clear to me.
It's clear, it's colorless. And look, there's a little bit of stuff dripping off the edge.
It's got a leak, I think.
It's dripping off the edge here, and that is liquefied oxygen and a little bit of liquefied nitrogen from the air. Very cool. But it does look like boiling water, doesn't it?
It does.
Now, did you notice something else? I poured a bunch of this stuff in here.
Where it's disappearing. Where is it going?
That liquid gained energy from the environment. Okay, this is a very warm room, and that liquid gained energy and it turned into a gas. We call that evaporation, and it's kind of hard to see how quickly that happens.
So it goes from liquid nitrogen to gaseous nitrogen.
Yes, just like, let's look the other way. Let's see if we can take some of that air that you had in that beach ball and slow down the molecules that are in there.
We can put this in the liquid nitrogen.
Unfortunately, I'd love to, but unfortunately this won't fit.
Oh,
but I do have a balloon here. I have a balloon, and we'll set that balloon in there, and that balloon has air molecules moving around
Whoa,
in there.
look what's happening to it.
And what happens is those air molecules,
It's getting shrinking.
their
It's
speed
shrinking.
slows down. The molecules don't shrink, but the balloon itself shrinks. And when we bring it back out of here, those molecules gain energy once again because of this room.
Wow,
Their
that's
speed
really
increases,
very cool.
and it comes back to what it looked like before. Pretty cool,
You
isn't
didn't
it?
take any gaseous
cool.
air out of there?
I didn't take any molecules out. I didn't put any new molecules
You just
in.
converted it from gaseous to liquid.
That's right, and warm gas to cold gas as well.
Wow.
All right, so now let's check this out.
What do you got for us
Let's
next?
watch to see how quickly this can evaporate. We were talking about evaporation before. So we have our buddy Oscar here.
So
we have our buddy Oscar.
What's the ratio between the volume between the liquid and the gas?
So the liquid that's in here, once it turns to a gas, it can expand up to about 600 times.
Wow, that's a big
So
expansion.
if I had a small cube of it right here, and I let it go from liquid to a gas, it would be like 600 of these cubes.
Wow.
The volume. So let's go ahead, and we're going to use Oscar here to help us out. He
All right.
comes along with us on nearly every set of demonstrations.
Oscar. Oh,
Oscar.
Oscar. Oh, here's Oscar. Yes, indeed. So we're going to pour some of this liquid nitrogen into here. Go ahead. I'll hold the funnel for you.
Oh, I can get the funnel.
Okay.
So this is a hollow copper tube. We're going to go ahead and put some liquid nitrogen in there. And then we're going to put a stopper in it. And we're going to allow that glove up there to capture all that evaporated gas.
Wow. So he's in there. Oscar's waving to us. I can see him moving.
He is. So you
Oscar.
can,
Oh, Oscar. Oscar, you've gotten big. Wow. You gonna give him some eyes so he can see us?
Yes. So that Oscar comes to life here.
Oh, there he
Okay.
is. Oscar's alive and well.
So everyone can wave to Oscar.
Hello, Oscar.
You can wave hello,
Goodbye,
or you
Oscar.
can wave goodbye. So the idea there is that the liquid in here gained its energy from the environment and turned from a liquid to a gas. And we capture that gas with this expandable glove.
Wow.
Notice we did not put this into something that can't expand.
That's a good thing because it would explode.
That would explode, and we don't want an exploding
That would make
device.
too much noise.
Now, the other thing-
You got to be careful not to stick your fingers in this.
I know
Now,
that.
what would happen if you just stuck your finger? I want to see you stick your finger in there.
Come
on, just do it for science.
No. You see that temperature right there?
Oh, that's really cold.
I understand that temperature is lower than inside my freezer.
Oh,
It's lower than on top of Mount Everest.
oh, that's cold.
And I know on top of Mount Everest, you can get something called
Frostbite.
Frostbite, that's it. And with frostbite, you can actually lose your finger.
Wow, that would be
I don't
bad.
want to do that. I think I would get frostbite
We need
if
our fingers,
if
okay.
I did that from here.
So do you have something you can stick in there, like a demo finger or something?
I do have a demonstration finger that we brought with us.
Oh, you did?
Yeah.
Oh, cool.
Check this out. And what we want to do is kind of see how cold this gets. Does it get as cold as a lump of clay? Does it get cold as an old rock? Or does it get cold like a chunk of glass?
Ooh,
I mean,
that's
as hard
cool.
as a chunk of glass.
Can I do this at home in my refrigerator?
You can try it at home, and I encourage you to do it.
Yeah.
I encourage you. Take a hot dog. That's what we have here, a hot dog.
Oh.
And go ahead and put it in the freezer. Next day, come out and slam it on the ground. I bet it'll break only into 1 or 2 extra pieces there. But watch this. This one
Wow.
breaks into
Whoa.
many, many pieces.
We have hot dog hors d'oeuvres.
We do. We do. Awesome.
Lunchtime.
That's all the time we have today in the States of Matter Lab. So Dr. Boom, I appreciate you coming by.
Well, I appreciate you showing me all these wonderful things.
Oh, it's awesome. Thank you. I like this little balloon.
That would really hurt my finger. Yikes. Anyway, we have a quiz now to see if you were listening to what they were doing in that lab.
All right.
Professor.
That's us. Dr. Boom.
Yes.
Welcome to the Plasma Lab.
Your plasma lab is beautiful.
Let's check this out because we're going to have to turn the lights off here in a moment. So I have a pump here. It's a motor and a pump that's actually pulling the air out of this tube. And we'll see what that looks like when the lights go off in a moment. And then we have a plasma ball here. We have some little tubes of gas that we're going to look at here in a moment. And we have another one over here, which is an electron beam, if we can get that to work, all right? So go ahead and turn the lights off.
Okay.
And we are going to check this out. Plasma, ionized gas. Now, let's take a look at this plasma globe that's down here, this little plasma ball. You can see I have my hand on here, and there's a stream of light that goes straight up to it. Or if I move over, it follows me. These are very cool, interactive. Now, what is a plasma? If we can remove some of the electrons that are around the nucleus of an atom, we can strip those away and we have positive and negative charges, then we have a plasma. Let me show you this a little bit closer. Same cameras, don't move the camera. And we'll just put this right here in front. Okay, I have a neon light here, that's one of those tubes. And I have a Tesla coil. This puts out high energy.
High voltage.
Yep, high voltage.
High voltage,
which is
30,000 volts.
Which is energy. So we're able to put some energy into this tube and turn the gas that's inside of there into a plasma.
Wow.
And when it relaxes, it actually gives off
So,
light.
Professor, why is it red?
This particular type is because of the electron transitions in the particular atom. This is neon, and it has a lot of red or orange colors that are given off because of the energy levels between the electron, where the electrons hang out.
Oh, that's the energy you're talking about.
Yes, and so, well, voltage is energy. And so let's take a look here. We have argon. This is a different gas. It's giving off light as well. And it gives off primarily in the bluish range, but it has other colors in it as well. Very cool, huh? So sometimes the students go and they see neon lights and the like, and it might be neon, it might be argon, but the idea is it is a plasma.
Oh, that was pretty cool.
Here's a fluorescent light. The white part up here is fluorescent. There's a chemical inside of here, coated on the inside. Down below shows the argon, and that argon has a little bit of mercury in there that gives off ultraviolet light. And that ultraviolet light excites this white coating in here. Very cool. A lot of good science right in your own home.
You can't see ultraviolet light though, can you?
That's true. You can't see that, but you can see the visible light that's given off there. And then one more thing, I took this light out of your desk. I took this little light bulb. It's a tiny light bulb. Well, not really that tiny.
Oh, it's an Edison light bulb.
It's a pretty good sized light bulb.
Yeah, it's an Edison bulb.
And it has a, we can make kind of a little plasma ball discharge in there.
Wow, that's pretty cool.
Okay. Now, let's take a look. So those are concepts in plasma. Let's take a look at this tall plasma column here. This tall plasma column, it has the same idea as what we did before. We've got a gas inside. We have gases inside. We have a power supply that's providing electrical energy into here, and we've made a plasma.
So what kind of gases are inside that?
So this one is just what we call an air plasma. So it would have nitrogen, like we talked about before, a little oxygen, like we talked about before, and a little argon in there.
So this would be like the aurora borealis or the aurora australis. This would be like the aurora tube.
Yes, this would be like the aurora tube that occur at the north and south pole of the Earth. Now, if I bring a magnet up to this, look what I can do. I can affect how that plasma is working. It's a little hard to see, but I have a little magnet here in my hand. Let's just show this little magnet here. So I've got this magnet that I'm moving back and forth here, and it's really affecting that plasma.
So the plasma is like at the ends there, at the bottom and the top, it's like following the magnetic field lines. That's exactly what happens in our fusion reactor when the plasma is formed. It follows the magnetic field lines like cars on a freeway.
That's right. That's right. Now, this is cool because, you know, nature let us know about this in the sense that scientists cannot do anything outside of natural rules and regulations, you might say. So this is one way that we can use to hold on to plasma inside of a tokamak. What did you say the temperature was in that?
It was 150 million degrees centigrade. It's so hot.
That's 10 times higher temperature than the center of the sun.
Wow, that's really hot.
That's awesome. So this is our air plasma in a tube, kind of showing a little bit of magnetic field interaction. Okay, magnetic field interaction.
So what do you have down at this end of the table? It's hard to see because it's so dark, but there's a gizmo down here. It's like a sphere with a power supply underneath it. And
that's right. So
what does this do?
That's our electron beam. That's our electron beam, and it takes a little while for it to get going. But this is a beam of electrons inside of a glass tube, And inside that glass tube, okay,
there you
inside
go.
that glass tube is actually a small, thin beam of electrons. Now, we can't see those electrons because they're tiny, but we have a little bit of helium that's inside of there. And I'm going to take this light away, and we're going to see if we can see that. The helium gets excited by those electrons and then gives off a blue light. And so then we can see the blue light of the helium. So let me go and remove this light. See if we can see that.
Well, I can see it with my eye. I can't see it on the screen, though.
Let me turn this up. There it is. There it is.
It's very dim, but it's there.
There it is. So that's electron beam, and I'm going to bring from the
that's good.
outside.
Look at that. Oh, beautiful.
That's cool. I'm going to bring a magnet from the outside.
Okay.
Wow,
bringing it. Look at that thing. It's moving all around.
And if I turn the magnet around, check it out. Check it out. It goes the other way.
Wow.
Okay, north or north, and south and south. If I bring it in from the front, I can make a little pigtail. I can move it all around. So the idea here, this is another demonstration that magnetic fields can have an influence on the trajectory of charged particles. We have charged particles, pluses and minuses, especially in our tokamak, and we have to use strong electromagnets to make that plasma go where we want to. Pretty cool, huh, Dr. Boone?
It is very cool. So this is like a plasma in itself, but it's a very low temperature plasma.
This is like a single species plasma. This is primarily electrons in here.
Okay.
That's right, rather than electrons and protons and ions and stuff. That's very cool. I think that's all the time we have from the Plasma Lab. So thanks for coming in and visiting, Dr. Boone.
Well, thank you for showing us all these wonderful demonstrations.
Oh, it's awesome.
Welcome to the D3D control room. D3D is the biggest magnetic fusion experiment in the United States, and it's right here in San Diego. As a scientist here, I spend most of my time when we're running experiments in the control room. Now let me give you a tour. When we're running experiments, this room is packed, and if you're a little bit late, sometimes you can't even find a spot. So this room is usually full of scientists, engineers who are involved in that day's experiments. They're often looking at data, or they're planning for an upcoming experiment, maybe in the next day or so. And so when you're on a RUM team, what we have behind us is these are all our real-time scopes. So that way, during a shot, we can actually see what's going on. We can fire a shot and we can watch real-time what is happening.
Thank you for interacting with us, and really thank you for joining us for this wonderful show. Just a quick shout out as our scientists and engineer get ready behind us. Shout out to this facility. Thank you for having us here. To the production crew that is sitting right here next to me with all this stuff. I mean, it really is just stuff. I mean, there's so much screens and cables and craziness. And Val Verde Unified School District and their production team, and to all of us involved. You'll see the credits at the end. But to finish off the show, the finale, I'm gonna turn it over back to the professor and back to the doctor for a little bit more.
Dr. Boone!
Professor!
This is awesome. We talked about states of matter. We talked about electricity and magnetism. We talked about how you can influence some particle trajectories using magnetic fields. What have you got here?
Well, remember back in the lab we were talking about, we levitated the coil on the aluminum?
Yes.
And
yes.
we were wondering if we turned it over and put the aluminum on the top. Well, we can do that here. We have a coil and we have the aluminum can on here. And we're gonna turn this thing on and show you what happens.
Is it gonna like jump up about a couple inches?
It'll go up at least
a few
couple
centimeters?
inches. Oh, I think so. So the way this works is there's a power supply here, and it charges up these capacitors under here, and the capacitors are like batteries that can be discharged real fast, but they have to be charged first, and it takes a little bit. And then we have a switch in this box over here. It's a little gap, a spark gap. And so then the current comes up out of the capacitors, goes through the coil really fast. Remember, moving charges or moving fields make things happen with conductors, okay?
Yes.
It induces eddy currents. So now, let's try this one here.
Oh, so you're going to run current through that to make a magnetic field in the white coil, and that's going to make a magnetic field in the bottom of the can, and so you're going to let that levitate about a couple of centimeters.
It'll levitate for sure.
All right, let's see how that works.
But it'll all go at once. Already. Countdown. 3, 2, 1.
Whoa!
Wow. So
that went way up there.
It went way up. We shot this off. It compressed the bottom of the can. If we had a fast action camera, we could probably see the can going up.
It went so fast. Now that's different than this one. What do you have over here?
Well, what I have over here is I have a can that we're going to stick in the middle. Now you know that when we turn on the field, that we repel the conductor, and so this is going to repel inwards. Okay, so we'll squeeze the can. Let's see how that'll go. We have about 10,000 volts. Ready? 3, 2, 1. Holy smoke! Wow, look at that can.
Oh, hold it up. Hold it still. Man, that is awesome. That actually ripped the aluminum apart. It made it so thin that it actually ripped it apart.
It did. A lot of force there.
So that's magnetic field interaction with real physical things. In this case, aluminum cans. A lot of energy in that.
So there you have it.
Wow. So I've got something for you, Dr. Boom.
What do you have?
Well, we went out hiking the other day and we saw a great big beautiful volcano.
Yeah.
And as you know, most volcanoes here on Earth are hot.
Yes.
But still, they have the same things, same attributes. They expand because of gases in there. They've got liquids and gases. I brought here the coldest volcano in California.
Wow, the coldest volcano.
Probably on Earth. Yes. There are colder ones on some of the moons of the other planets, but not here. So let me show you. So I have some soapy water here. It's very simple. Very simple, soapy water.
Soapy water.
I'm going to pour in a little bit of liquid nitrogen.
Yeah, you're bringing it. This is the line. This is the line you're bringing it to here.
That's the line I'm going to bring it to, and if I can bring it to here, well, you know, that's about 30 or 40% of this, and I say that would make a good volcano.
Yeah. Okay.
If I can just bring up the bubbles and stuff up to there.
Just like the lava flows over.
That's right.
Okay.
So let's go ahead and check this out. Let's get a countdown.
3, 2, 1. Whoa, look at that.
Uh-oh.
I thought you were just going to bring it up to the line.
I made it to the line. There's the line right there. And look what we actually have. We do have gases. We have gases. There's some liquid I can see down there.
Gases.
And then
the liquids.
And then I can put my hand in here and pull out some ice, which is actually a solid.
3 states of matter.
So for this one, we have solids, liquids, and gases. It happened from an expanding gas. I'd say this is a pretty good volcano.
Absolutely.
All right.
And you could do it in your house.
Well, if you have the liquid nitrogen. But nevertheless, science is awesome.
Absolutely.
We've learned a lot today. We've learned about magnets and states of matter. We appreciate you being here for STEPCon20. This is Professor Matters.
And I'm Dr. Boom. Remember, science rocks.
Thank you.
Hold on, hold the fort. Okay, we are very grateful and thankful to be in this facility, and thank you, gentlemen, for that great show. That was awesome, and it's awesome to be here. But we also want to give some recognition today for the hard work that these gentlemen and the other scientists here have put in, for their generosity and for their tireless efforts. I'm going to ask Gordon Borns, the chairman of the STEP board, to come up.
Okay. Thank you, Carlos. So it is my honor, my pleasure to introduce and present a plaque to Rick Lee. He is the chief operator here at the D3D Tokamak research facility in San Diego. So this is for the 20th anniversary of your participation in the science show.
Thank you,
so
Gordon.
Thank you very much, Rick. And Alex Nagy, I have a plaque for you also. I wish I could shake both your hands.
Yeah, thank you very much.
Alex is in charge of special engineering programs here at the D3D Tokamak. Also, I have a plaque too for Genevieve.
Genevieve,
the Grand Champ. Genevieve, the Grand Camp. Genevieve, here is a plaque for you. Thank you very much. And a plaque for Mitchell Clement.
All right, Mitchell.
Hey, Mitchell.
Mitchell, thank you very much for your role in the science show. And Rigo Brambilla. Rigo, please join us for your certificate. And Rigo is one of our technicians here at the D3D Tokamak. So thank you very much, General Atomics team.
Thank you, Gordon.
And thank you for a fantastic science show too. Our first online science show for STEP.
Thank you.
And now, goodbye and have a wonderful rest of your day.
Thank you. Appreciate that.
Absolutely, thank you. I wish I could shake your hand.
That was a great show, wasn't it? Oh, we learned so much. Just make sure that you check out all the resources we have on our website, that your teachers look at the teacher packet for everything that's there. All of this is being recorded so you can see it later. So thank you again. Keep learning and keep stepping ahead. Have a good one. Bye from San Diego.